So we're going to start session 3. We're going to discuss power, energy, and resistance. Again, power, energy, and resistance. So far we have discussed current, we have discussed voltage, and also resistance. We're going to go in detail and talk about power, energy, and also resistance. So session 3 will cover the following topics. Review the fundamentals of electrical energy and current. Also, we'll discuss energy use, energy sale, energy storage, how is energy produced. We're also going to discuss power usage, power rating, and also power conversion. So power is a term that we hear a lot. We will discuss power and also energy as well. We want to apply the knowledge of electrical fundamentals to solve basic problems. So now we begin more of our problem solving. We want to also describe the generation, transmission, and storage of electrical energy. So again, just like in our first lesson, we talked about efficiency. Now we're going to talk more about energy generation, looking at the different sources of energy in terms of solar or hydro, and so forth. At the end of this session, we want to evaluate the benefits of electrical energy over other forms. We want to be able to articulate that. Why is electrical energy preferred to heat energy and so forth? We also want to calculate the energy usage for electrical appliances based on their power ratings and also on their usage times. Then we want to calculate the energy efficiency of an electrical vehicle given the power rating and its components and duration of operation. So we want to calculate the energy usage, innovating in that space. And now we have the whole industry going towards electrification. And so we have a problem where we'll look at the electric vehicle. So for this session, I shared with you chapter 4 in the presentation. We will come back to chapter 3 later on. So let's go ahead and go to our next page, which is the content page. All right, so step 1, we are told to review this presentation. So I'm going to just go ahead and download it. Energy. So the unit for energy is, we have the joule. The symbol that we use to represent energy is W, or you can say it's work. Energy is the ability to do work and is measured in joules. 1 joule is work done when the force of 1 Newton is applied through a distance of 1 meter. So if we take the force of 1 Newton and we move it for a distance of 1 meter, that is said to be 1 joule of energy or work. The symbol for energy, W, represents work, but should not be confused with the W, which stands for power. So the unit for power is the watts, right? So power is measured in watts, and we use the W, but when we discuss energy, we also use W as well. All right. Another unit that we use to describe energy is measured in joules. Energy is also measured in kilowatt hours, right? Kilowatt hours. What is the kilowatt hour? The kilowatt hour is much larger than the energy. Sorry, it's a much larger unit of energy than the joule. There are 3.6 times 10 to the 10 joules in a kilowatt hour. So on your electricity bill, the energy sells you power in kilowatt hours. That's the unit that they use to measure or to sell you, to sell energy to you, right? Again, we can convert kilowatt hours to joules and joules to kilowatt hours. Here you can see here. The question asks, what is the energy used in operating a heater of 1200 watts for 20 minutes? We're asking what is the energy that is used to operate a heater operating at 1200 watts for 20 minutes. And here, 1200 watts is the same as 1.2 kilowatts. And so what we do here, we are going to multiply the power. Now, we did not describe powers yet. We only described energy and work. So here we are using the unit for power, which is the watt, and we are multiplying that by the amount of time that the equipment is being run, which is 20 minutes. So we convert minutes into hours so that our final units are going to be kilowatts hour. So here you can see we multiply 1.2 kilowatts by 1/3, 1/3. 20 minutes is 1/3 hour, right? Because we have 60 minutes in 1 hour. So 1.2 kilowatts by 1/3 hour, and we get 0.4 kilowatt hours. So again, based on unit analysis, we multiply kilowatts. We need to convert the power into kilowatts, and then we need to convert the time into hours so that our unit is going to be in kilowatt hours. Okay, so now we already used the unit for power. Let's describe what power is. Power is the rate at which energy is used. Again, the rate at which energy is used. Now, there's a law called the law of conservation of energy. It says that energy cannot be created or destroyed, but can be converted from one form to the next. Now, we also described efficiency earlier in the course. We said that the way we use electrical energy is that most times we convert the electrical energy into other forms of energy so we can use it. Like a light bulb, we convert electrical energy into light. A heater, we convert electrical energy into heat. For anything that requires motion, we convert that electrical energy into kinetic energy and so forth, right? So we convert energy from one form to the other, right, that is desired. And we talked in efficiency, we said that, well, the conversion is not 100% in the desired form. We have some that is converted into some other forms that are not desirable, and we can consider them waste, but that leads to us not having 100% efficiency. Now, power here, when we describe power is the rate at which energy is used, or the rate at which energy is converted into another form, right? Power is the rate at which energy is used, or the rate at which energy is converted into another form. And so you will see this, right? The faster we use energy, or the faster energy is converted to another form, the higher power we're going to have, right? The slower energy is converted, we're going to have a lower power. So again, the unit for power is watts, and sometimes we use the kilowatts as well. Notice the rate always involves time. So power is the rate. Anytime you hear rate, we are getting a difference, and we're dividing it by time. Power is the rate at which we use energy. How fast are we using that energy? So it's going to be the amount of energy divided by the amount of time, how fast we use it. And so the unit for 1 watt is 1. If we use 1 joule in 1 second, we have 1 watt. So if we had 5 joules and we use that 5 joules in 1 second, of course it's going to be 5 watts. 3 equations for power in circuits are collectively known as Watt's law. So how do we calculate power? If we have a circuit and we know the voltage and the current, we can multiply them and we get power. If we have current and resistance, we can also calculate the power as well. And if we have voltage and resistance, we can also calculate the power that is used. Power tells us how fast energy is converted from one form to the next. And we have some examples here just to show you what we're talking about. So example 1 says, what power, in other words, how much power is dissipated in a 27 ohm resistor. Now, as we go forward, what does a resistor do? We said a resistor is a device that's manufactured to have a fixed amount of resistance, right? In essence, a resistor converts electrical energy into heat, right? So like a resistor is a heater. It converts electrical energy into heat. So it is converting it from one form to the next, right? So we're asking the question, what power is dissipated in a 27 ohm resistor if the current is 0.13 amperes? Now, of course, we're going to use the equations that we just looked at on this page. So again, we're asking, okay, what is the power that is dissipated by this resistor? Like, how fast is this resistor converting energy into heat? And so to get that, our answer here, we're going to use power is equal to I squared R. And so we get 0.49 watts of power is being dissipated by this resistor, right? Another example, what power is dissipated by a heater that draws 12 amperes of current from a 120 volt supply? So we have a heater And again, what does a heater do? It converts electrical energy into heat, right? And we're saying, okay, what is the rate at which the energy is being dissipated? What is the power of that heater? And so to do that, we use the equation power is equal to current times voltage, and we can see that the power of that heater is going to be 1440 watts. Again, remember, power is how fast we use energy, the rate at which we use energy. Another example says, what is the power dissipation of a 100 ohm resistor with 5 volts across it? And again, we can use the other equation that we have for power. Power is equal to V squared over R, and we have 0.25 watts. Here we say small resistors operating in low voltage systems need to be sized for anticipated power. What does that mean? All resistors, I think we have a picture here. Hold on. Okay, the picture is not there. So, small resistors need to be sized for the anticipated power. What that says is that anytime you have a component, your component has a rating, right? A power rating. So, say for example, I have a 100 ohm resistor. I can have a very small 100 ohm resistor. I can have a very large 100 ohm resistor. The size of these resistors tell me something about the rating, right? How much power each component can dissipate. And so in our circuits, we want to make sure that when we buy a resistor to put in the circuit, that the resistor has the correct power rating. So in our circuits, when we calculate the value of resistors, we also will calculate the power rating of that resistor, so that if we were to build a circuit, we will build it with the right component. After we get the power rating, we also need to multiply a safety factor by it, and that safety factor helps us to be more safe with the circuit, because it's now rated above what it can dissipate, so that in the event it moves slightly up or down, we're not going to have a failure. So we'll talk about power rating again, and it may come up in your quiz as well. Continue. So resistors can be damaged, and we have an example here. It says resistor failures are unusual except when they have been subjected to excessive heat. Now again, excessive heat tells you excessive power has been dissipated in that resistor, and it's not rated for that power, so it's going to become damaged. Looking for discoloration, sometimes the color bands appear burnt, and then of course you can test that resistor with an ohm meter, and if it's overheated or if it's damaged, most times it's going to appear as an open, right, with infinite resistance. So again, here we have a digital multimeter, and of course you can have the digital scale here, or you can have an analog scale where you have a needle that is moving as well that you can use. Of course, notice here you have the screen, and you also have the selector that you're going to use. Following this, you also have some ports at the bottom where you may need to put your leads so that you're connected to the correct circuit. Okay, ampere hour ratings of batteries. So again, when you buy a battery, most times you will not only look for the voltage, but you need to know, okay, well, how much energy does this battery have, right? What is the ampere hour rating? So we don't use kilowatt hours, but we use ampere hour ratings. Expected battery life of batteries is given as ampere hour specification. Various factors affect this. So this is an approximation. Factors include the rate of current withdrawal, the age of the battery, temperature, etc. So here's a question. How many hours can you expect to have a battery deliver 0.5 amperes? If it is rated for 10 ampere hours, so again, if it's rated for 10 ampere hours, and we divide this ampere hours by 0.5, we are going to have 20 hours, right? So again, when you look for a rating of batteries, if you buy a battery to put in a circuit, say in your phone, the rating for the battery is in ampere hours, and that tells you how much current can be. So you can use that to calculate how long your battery is going to last based on the amount of current you are drawing from it. Power supply efficiency. Again, we have the term efficiency come back up. Efficiency of a power supply is the measure of how well it converts AC to DC. For all power supplies, some input power is wasted in the form of heat. So here we have an efficiency example, but we are using a power supply, a DC power supply as that example. So what does a DC power supply do? It takes the AC from the wall, which is normally 120 volts, and it converts that AC into DC at a voltage that is desired. For example, let's look at the phone charger. The phone charger takes the wall AC and it converts it into DC at 5 volts, probably at 2 amperes, so that you can charge your phone with, right? So we are saying efficiency is the measure of power, total power in versus total power out. So again, we're saying in your power supply, we're going to have some energy being dissipated as heat, right? And so our total power out is not going to be equal to the total power in. We're going to lose some energy because it's going to be converted into some other forms that are not desirable. And so we can actually calculate the efficiency by having the total power out, which is the desired power, over the total electrical power in. Here's a question. What is the efficiency of a power supply that converts 20 watts of input power into 17 watts of output power? And so the answer is going to be output power over input power. So it's 17 over 20, and that gives us 85% efficiency. Of course, the best thing is to have 100% efficiency, but we want to go as close to 100% as possible. So this is the end of presentation 4. Let's go over the quiz quickly. The SI unit, okay, a unit of power is, so again, a unit of power, we said that there are 2 units for, the unit for power is the watt, right? We said that for energy, we said that the unit for energy is the joule, and also we can have the kilowatt hour as a unit for energy, but the unit for power is the watt, right? What is the SI unit of energy? It says the SI unit of energy is what? And in this case, it's going to be the joule. Okay, and I can double check this. Number 2. Okay, number 2 is B. So the SI unit for energy is the joule. If the voltage in a resistive circuit is doubled, what will happen to the power? If the voltage is doubled, the power will also be doubled. Remember, we had we saw the equation that power is equal to voltage times current. So if you multiply the voltage by 2, the power is also going to be multiplied by 2 as well. Okay, because voltage is directly proportional to the power. The smallest power rating. So again, power. What is power rating? Okay, so if you have a resistor, we can calculate, okay, how much power does the resistor use? And then we multiply that by a safety factor of 20%. So we multiply that by 1.2, which is 120%. And then we get our power rating that we're going to use. So when we buy the resistor, we're going to buy it with the power rating value. So if we have a resistor of 340 ohms with 12 volts across it, we are saying what is the smallest power rating we should use for this resistor? That power rating is going to be, first we need to calculate the power, which is going to be V squared over R. So 12 squared over R. So I'm going to, let's pull up my calculator. Let's calculate this quickly. So 12 squared, so V squared over R, that's the equation. You can go back and look at it. So 12 by 12 will be 144. 144 divided by R, 330. And so the amount of power that this resistor uses is 0.436 watts. Now I need to multiply this by 120% so I can have the safety factor of 20%. So I'm going to multiply it by 1.2. And so this is the power rating. So you can see that the power rating is 0.5 to just over a half, right? And so since this, for small resistors, the power rating is normally in like fractions of a watt. So you have like quarter watt, half a watt, 1 watt, 2 watts. So if our power rating is 0.5, we are not going to take the half a watt, but we're going to take the next power rating, right? So we're going to take the 1 watt resistor to use in that application. So again, we calculate the power, then we multiply it by the safety factor, and then we select the rating of the resistor. So our answer is going to be the 1 watt resistor, which is the next one higher. The power dissipated by a light operating on 12 volts that has a current of 3 amps. Now again, the equation for power, so of course I expect you guys to make some notes. For example, you need to copy down all the equations for power so that you can know them, so you can use them. You need to take down the equations for current, voltage, and resistance that we talked about earlier, the equations for energy, the equations for voltage, and for current, and probably I'll share them at the end of this course, at the end of this lecture. So again, the equation that we can use is power is equal to voltage times current, and so we're going to have 12 times 3, which is going to be 36 watts. The power rating of a resistor is determined by the surface area. Also, the bigger the component, most likely the higher the power rating of it. So again, we can have a small 100 ohm resistor like this. We can have a big one like this. Both of them have the same amount of resistance, but the bigger component is going to have a higher power rating. So the size, energy and power. So I have a short write-up here for you. Electricity is the flow of electrical power or charge. Electricity is both a part of basic nature and one of the most widely used forms of energy. The electricity that we use is a secondary source because it is produced by converting primary sources of energy such as coal, natural gas, nuclear energy, solar energy, and wind energy into electrical power. Electricity is referred to as an energy carrier. That means it can be converted to other forms of energy such as mechanical energy or heat. The primary energy sources are renewable and non-renewable energy. But the electricity that we use is neither renewable nor non-renewable. So again, let's look at these definitions here. Power is the rate at which we use energy. If we use energy quickly, we said we have a higher power. If we use it slowly, we have a lower power. For example, if you look at 2 light bulbs, right? I like to use light bulbs. Very easy example. If you have a light bulb that gives off a little bit of light, so it uses, say if you have 100 joules of energy, it uses 100 joules of energy over 100 hours, right? So the rate at which it uses energy is 1 joule per hour. Again, you have 100 joules of energy, it uses the rate at which it uses energy is 1 joule per hour. That is its that is its power, right? Now, of course, power is joules per second. Okay. If you have another light bulb that uses 100 joules in 1 hour, of course, the power is going to be higher for that component. So again, the faster, the more energy a device uses, the faster it uses energy is going to be, the power rating is going to be higher. If you think of a blender, you think of your iron at home, all of them are rated for about 1,000 watts, right? Because they use a lot of energy quickly. Energy is the capacity to do work. Electricity is the measure of the conversion of energy from one form. Efficiency, is the measure of the conversion of energy from one form to another. Electrical conductors are used as conduits to transmit the energy from locations where applications are needed that can convert the energy into needed form. So when you think of the electrical installation in your home, you have all the circuits bringing different outlets, different places in your room. You have a circuit for your light switch, a circuit going to your light bulb, circuit for your heater, and so forth, right? And all of them go to a central panel where the electricity from the power company comes in to the circuit breakers, which act as protection devices. All these circuits all over your home, they transport energy to the places where you're going to use it, right? Where you're going to convert it from one form to the next, where you're going to use that energy in desirable forms. It says this article shares insights on sources of energy that are used in the United States. So I'll click on it here, but we're not going to read the entire thing. I'm going to leave it for you to read. So again, this is from the U.S. Energy Information Administration, and it describes the types of energy that are used in the United States in terms of what are the sources, what is renewable and non-renewable, etc. So I'm going to leave it for you to read, right? Here you can see in this graph that most of the energy that is used, about 45% is petroleum. Following that, we have natural gas, we have nuclear, coal, and also we have renewable at 12%. And of course, you have the different types of renewable. We have geothermal, solar, hydroelectric, wind, biomass waste, biofuels, wood, etc. Okay, there are 5 energy use sectors. So you have electrical power, you have transportation, you have industrial, residential, and also commercial as well. So energy is a very important topic to be concerned about in terms of not only energy security, but also in terms of conservation of energy, in terms of, especially with the climate change push, in terms of achieving carbon neutrality. So I will leave this article here for you to read. I have a quiz that asks you some information about this, so it will quiz you on it to ensure that you have read it and that you are familiar with the points inside. Okay, let's continue. Coming to an end. Using energy tools for renewable energy and storage planning. Okay, using energy tools. Now, of course, energy is a broad interest, is their interest in education as well. So the Department of Energy puts out a number of tools, there are a number of initiatives so that students can be involved in energy, so that they can even desire to work in the energy industry, whether it is on the generation side or on the policy side. So from any background, energy is something that is interesting to know. There are also job opportunities available in energy as well. There are incentive programs for citizens to install their own renewable energy system for the energy needs. This helps reduce dependence on grid and can help reduce the energy cost in the long run. Energy storage solutions are also being used for some systems to store energy for non-generation times and peak demand times when the price of energy is the highest. The solution for home storage range from customer-owned battery banks to commercial products such as the Tesla Powerwall. There is also the novel concept of using electric vehicles as energy storage to power homes during peak demand hours. The design of a system should take into consideration the energy usage, estimated energy produced by alternative energy. The Department of Energy has provided a tool called PV Watts that is used to estimate the capacity of a solar system for a home. And so I put a link here so you can check it out as well. We also have a video on how you can use PV Watts. So it's a tool online. You put in the size of your roof and it gives you some information. You put in some of your usage, and I think it gives you recommendations on a solution that you can use. If you were to install a solar solution, it gives you information that you would use to go about this. On the other information, I have here a battery life calculator that you can get from DigiKey. So here it simply allows you to enter the capacity of your battery and your consumption, and you can calculate, how long your battery will last. Now, DigiKey is a website that sells electric components. They also sell energy solutions as well. So there are tutorials on there that you may find useful in the future. And the next link I put here is about an electric go-kart. Let's continue to the site here. Okay, so this is just a small project about creating an electric go-kart. What are some things you would need, right? Okay, and this is just for your review. Let's go to the last page, which is the assess page. So what are the equations that you need to know? Equations. First one, we talked about current, right? We said current is the amount of charge that flows per second. So the unit for charge, the symbol for charge is Q. And so of course that's going to be, and here's an example, 10 coulombs in 5 seconds gives us 2 amperes, right? So this is current. What about voltage? We said voltage is the amount of energy that we use per coulomb of charge that flows. So E over Q or W over Q. And so here's an example. If we have 10 joules per 2 coulombs, we have here 5 volts present. Secondly, we said that, which is this Ohm's law. Ohm's law is the relationship between voltage, current, and resistance. So we can say that voltage is equal to current times resistance. And of course, it's a simple algebraic equation. So we can say that current is equal to voltage over resistance. And we can say that resistance is equal to voltage over current. The other, so again, this, you need to know this, you need to know this. You also need to know for power as well. How do we calculate power? So we said power is equal to how fast we use energy. So it's going to be energy. And so I'll use W to represent energy over time, right? So if we have, so here's an example. If we have 10 joules of energy and that is used or converted in 1 second, then we said to have 10 watts of energy, 10 watts of power, right? And as we said, the other way we can calculate power is equal to voltage times current. We said, again, if you just substitute Ohm's law in here for voltage, for example, if you replace voltage with I times R, you're going to say that power is equal to I squared R, right? Again, if you replace voltage with I, you're going to have I times R times I, so you have 2I, so I squared times R. We also said that power is equal to voltage squared over R. So if you replace current with V over R, you're going to have V over R times R, right? So we have V squared over R. That's so these 3 equations we use for power. Now we also talked about the power rating. What is power rating? When we calculate the power of a resistor, we need to multiply it by, it's going to be power times 1.2. So it's like you multiply this by, if you multiply something by 1, that's 100%. If you multiply it by 1.2, that's 120%. So power rating is 20% over the power that the component uses, and that gives us our power rating. So if we had a power of 10 watts, the rating is going to be 10 times 1.2, which gives us 12 watts. That's the power rating. So before we end today, let me just give you an example. So let's say we have a circuit with a battery and a resistor. And our voltage here is 10 volts and our resistor is, let's say we have 5 ohms on the resistance, right? Okay, so this is our circuit here that you were given. And we're told find current. So how do we find current? So what's the current that is flowing? We can use this equation here, V over R, right? So current is going to be equal to V over R, which is going to be 10 volts over 5 ohms, which is going to be 2 amperes. Then we are told, okay, go ahead and find the power in the circuit. What is the power that is dissipated in this resistor? The power is going to be equal to V times I, or since we have this here, we can actually use this, right? So, but let's just go ahead and use these two here. So we will use V squared, power is equal to V squared over R. So power is equal to V squared over R, and that gives us 10 times 10, which is 100 over 5 ohms, and that gives us what? 100 divided by 5 is 20. Okay, so this is 20 watts. Let me just verify. All right, so this is 20 watts. Okay, if you use any other equation, for example, if we said that power is equal to V times I, we would get the same thing, right? So V is going to be 10 volts, I is going to be 2 amperes. We would also get 20 watts. Now, if I told you find the power rating is going to be P times 1.2, which is going to be 20 times 1.2, which gives us 24 watts. So this is the power rating. Okay, this is all that we have discussed so far. So this equation, like I said, you need to know, you needed to answer the questions. For voltage, that power is equal to energy. Let's put the work here. Energy over charge, that's for voltage. Then you also need to know that voltage equals to current times resistance. And you need to know this one as well. Then you also need to know that power is work over time, the rate at which we use energy.